So another enzyme called topoisomerase, so that's Topoisomerase. So that works a little bit beyond the strands here. So that works out the little kinks and prevents it becoming too tangled to make it easier for the helicase to unbind it. So it does that, and so it turns it and then makes it easier for the helicase to do that, to do its job. Another enzyme that works in is DNA polymerase. So it's only able to add nucleotides to the 3' end of an existing DNA strand. So the enzyme primase makes a short RNA sequence. It's just about like 10 to 15 units long of RNA. So it's an RNA sequence. And there's like a short little thing to get it started. So it's 5' to 3', right? So it adds that, and then the DNA polymerase 1 would add DNA to this end of the strand. I don't know if you can see that, but it would add it to this end of the strand. So it uses the existing DNA as a template to create the new RNA part. And then the DNA polymerase 3 continues to add the DNA to this side, and it forms most of that. And then we get, before we can do that, the DNA polymerase 1 has to eject the RNA primer. So this gets like, pew, away from the rest of the sequence, and then DNA replaces it. So no more RNA, and then there's DNA now. So when the primer gets put in there to get it going, and then it gets ejected, and then RNA goes out, and then DNA goes in. So it's all DNA and no RNA, because RNA is not what our genes are made of, really. So there's another component in the replication process, and that is the leading and lagging strands. So remember how DNA polymerase can only add DNA in a 5' to 3' direction? Well, this gets kind of complicated now because of the replication fork. So remember, the replication fork is a little Y-shaped structure. So at the replication fork, actually, let me draw this the other way. So here's the replication fork like this, right? And then it goes from a 5' to 3' direction. So let's just put 3', 5', and then since this is 5', this has to be 3' because it's anti-parallel and complementary, right? And then this would be 5'. And so, when you're going in the leading strand, it would go in a 5' to 3' direction toward the replication fork right here. So the new strand is 5' to 3' in the direction toward. So this is the leading strand here, because it's going in a 5' to 3' direction toward the replication fork, which is right here, that Y-shaped area. And then in the lagging strand is made of Okakashi fragments, so they're broken apart because the RNA primer has to detach and reattach at this new area that's being revealed. So each of these segments needs a RNA primer to get the DNA replication going again. And these are the lagging strands. And so these are not continuous. As you can see, they're broken apart, and it goes in the opposite direction. So it's 5' to 3' direction away from the replication fork. So it's moving away. So again, 5' to 3' toward the replication fork is the leading strand, and it's continuous, and it only needs one RNA primer. But away from the replication fork, it needs a primer for each little broken piece of fragment. So it's discontinuous, and it goes from 5' to 3' away from the replication fork. And then we have another enzyme called ligase. It would meld these two leading and lagging strands together. So like mush them together like that, and then it would also take the 3' of the primers and attach it to the leading strand. So remember the primer that we had here? The 3' part, it would attach it to this continuous part, so you'd have one full DNA strand.